In this presentation, I will talk about panel data models. The outline of this presentation will be to talk about panel data setup and variations, and then we will talk about different estimators, the pooled or less model estimator, the first differences estimator, the fixed effects or the within estimator, dummy variable regressions with fixed effects, the random effects estimator, and then we'll finish up with the Hausman test for deciding between fixed effects versus random effects. So when we have panel data, it's because we have panel data variables. So we would distinguish between three types of panel data variables. The first type is the varying regressors, XIT. And examples could be annual income for a person, monthly food expenditures. Here we have the variable and then I and T, which means that this variable varies for the individual and over time. Then we would have time invariant regressors, where xit would be equal to xi for all t, variables such as gender, race, or education. Now, it's possible that someone in the sample could get more education, and in this case, we will not have time invariant regressors, but if no one has variation in the sample, these would be time invariant regressors. And finally, we have individual invariant regressors. This is when xit equals to xt for all I. And these would be variables such as a time trend or US unemployment rate. That would be the same numbers for all of the individuals in the sample. Okay, so now let's define different variations that we have. First of all, xit would be the individual value. Xi bar would be the individual mean, and X bar would be the overall mean. So in this case, xit would be varying for each individual and each time period. And then xi bar, that would be the individual mean over time. So a mean taken for each individual over time. And X bar would be the overall mean, which means that the average is taken across all the individuals and over time. So when we talk about the overall variation, this would be over time and individuals. And so the overall variation would be the individual value for each variable minus the overall mean. For the between variation, we want to know how does one value for one individual differ from the overall mean. So here we would have xi bar, which would be the average for a person, minus x bar, which would be the overall mean. So here we're showing how the average value of the person differs from the overall mean, or this is also called the variation between individuals. And then we have the within variation, so that will be the variation within the individual over time. And here we would have when the individual value xit, how that differs from the individual mean. So basically, is the individual value higher or lower than the average for this particular person? So we would call this within variation because it's within the same individual, within the individual over time. The between variation is basically between individual, from one individual to the next, and the overall variation involves both variations over time and individuals. Let me give you some examples. So here's how an example of an artificial panel data set that I'm going to use to illustrate these concepts. So here we have ID, this is the cross-sectional dimension I, and the time dimension T. So here we have individual 1, 2, and 3 in the data, and then we have 3 years of data for each individual. And let's suppose that we have a variable that varies just like that, and I picked convenient numbers here that would illustrate the points. If we're to calculate the individual mean xi bar, we would have to calculate the mean over these three variables, which is 10. So I have repeated 10 here. The individual mean of 20 is 20, and the individual mean of these three numbers is 30. So the overall mean would be the mean of these means. So the mean of 10, 20, and 30 is 20 for the whole sample. And you see how it's the same number for all of the individuals and across time. So now we're ready to calculate each of the deviations because we have the individual value, the individual mean, and then the overall mean. So the overall deviation is the individual variable minus the overall mean. So here we have this value minus the overall mean is this one, and we have this value minus this value is that, and so forth. These value minus this value is that one, and so on. So here is we have a deviation of each of the individual value from the overall mean. Now for the between variation, we would be picking up the individual mean, this one, minus the overall mean. So we would have this minus that is here, this minus that is here, and this, and so on. So notice that for the between variation, we actually don't have any variation over time. Why? Because we don't consider the variation over time. We only have between the individual. So this first individual is 10 units below the overall mean. This one is right at the mean, and this person is 10 units above the mean. So now that's on average. So now this is on average across all of the values. And finally, for the within variation, we're doing each of the individual variables minus the individual mean here. So we have 9 minus 10 is minus 1, 10 minus 10 is 0, 11 minus 10 is 1, and so forth for the rest of the numbers. So here, what all we can say is the first individual here is 1 unit below their mean of 10. Here they're at their mean, and here they're 1 unit above the mean. This individual doesn't vary over time, and this individual is 5 units below the mean in the first year, and in the third year is 5 units above the mean. So that's the within variation of how each variable varies over time. So notice that we also lost the general level of what was the level of the original variable. So we only consider, is it higher or lower than the average for this person? So some computer software such as Stata use the within deviation as modified. So it's not exactly this, but it adds back the overall mean. So this number here, the overall mean. And so we have this plus the overall mean of 20. So it basically boosts up all of these values here to a level that is based on the overall mean. But that's not obviously the mean of each person. It's just the overall mean. And the final column here considers first differences. So here we have xit minus xi t minus 1. So this is basically how we calculate the first difference. So we take each value minus for an individual minus the value for this same individual in the previous period. So here for the first observation, we have dot missing value because we can't take the difference with the previous period. Here we have 10 minus 9 is 1, and 11 minus 10 is a 1. And again, same calculations for the other people, and this is how we have the first differences. The pooled OLS estimator uses both the between and within variation to estimate the parameters. So what we do is we stack the data over I and T into one long regression, and we're estimating the following equation. YIT equals beta 0 plus beta 1 x 1 IT plus beta 2 x 2 IT plus UIT. So here we have basically n times t observations, and we have again one long regression where everything is stacked together, and we're basically ignoring the panel data nature of our data set. So for this reason, this estimator is not used very much since we need to account for the fact that we have panel data. The next estimator that we will consider is the between estimator. And this estimator uses the between variation, that is between individuals. It uses the time averages of all variables. So instead of using the original variables, we would take the average of each of these variables over time. So this is why there's no T subscript here, because this average is taken over time. So this is how a between estimator would look like. Notice that everything here, all the variables have a bar on top of that. So here we would have n observations because we would be taking the averages over time for each of these observations. So this is rarely used because the panel data essentially gets collapsed over time, and we're not using the richness of the data set to estimate panel data models, but only the between estimator that considers the variation from one individual to the next, but not over time. Then we have the first differences estimator. And so this estimator would use the one period changes for each individual. So let's start with the panel data model that we have here. Notice that I have introduced here AI. AI would be individual specific effects that are unobserved factors that are attributed to each individual. So therefore, we don't have the data on it. We cannot model them, but there's something about individual I that would make their dependent variable higher or lower. And that's what we would call individual specific effects. So in order for us to try to eliminate this effect from the equation, what we would do is we would take first differences. So we can also estimate this model with the data for t minus 1 and take the differences like that. And then we would have yit minus yit minus 1. So this is effectively the first differences or change in y that we have taken over time. And here we would be doing the same for all of the independent variables. So we would be estimating this model for using OLS, and we would be using one period changes of the dependent variable and independent variables. Here the number of observations would be n times t minus 1 because the first period would be missing because of the differencing. Note that the individual specific effects AI cancel out because if we have AI in period t minus AI in period t minus 1, well, it's the same effect because it doesn't vary over time, therefore they drop out. What also drops out is time invariant variables, and their coefficients are not estimated. So if we have a variable like education that does not change for the individual in the data set, then such variables would be dropped from the model because there would be 0 for every individual, and therefore their coefficients cannot be estimated. So now let's talk about fixed effects or within estimator. So this fixed effects estimator would use the within variation. And this variation would be within the same individual over time. And we would be using what we would call time demeaned variables. So let me show you how. If we start with the same panel data model that has individual specific effects AI, let's suppose that these individual specific effects are potentially correlated with the independent variables. So maybe you can think of these individual specific effects, a variable such as ability of an individual that is not observed but affecting the dependent variable, say wage. Well, if we cannot observe it, it cannot be included in the model, but such individual specific effect may be correlated with the independent variable, say education, because more able people are more likely to have higher education. So that's a very reasonable assumption to assume that this individual specific effects are potentially correlated with the independent variables. That's why we cannot leave them and ignore them and leave them in the error term, because now our error term would be correlated with the independent variables, and that would produce biased coefficients. So our goal is to eliminate these individual specific effects from the model. How are we going to do it? That's the procedure. We would take the time averages, which is basically taking the averages over time. So notice that this is the same as this, except that all of the variables are now averaged. Okay, and so now we would be subtracting this equation from this equation, and this is what we are going to find. Each of the variable minus its mean. And what we will also accomplish here is that these individual specific effects would drop out because it doesn't vary over time. Therefore, they would be the same for each individual and they would drop out. And so we're calling these variables now the time d-mean variables. Why? Because we are taking the mean over time and then we're removing it from the original variable. So this is why if we take the mean away, we're calling that d-mean variable, and it's time d-mean because it happened over time. This average is taken over time. So this is why this variable here, the variable minus its mean over time, it's also called a time d-mean variable. So this would be a fixed effect within estimator. So instead of estimating the original model, what we're going to be doing is we're going to take each variable minus the mean, form these new variables, and that's how we are going to estimate the model. So again, the advantage of that would be this time d-mean model would not include the individual specific effects AI, and therefore it can be estimated by OLS. The number of observations here would still be n times t, and the within estimator also cannot include time invariant variables because they will drop out. So again, the example of education, if it does not vary for individuals in the sample, so if no one got additional education, the education in each year, the number of years of education minus the mean would basically be a 0 for everyone. So such variable would drop out, a time invariant variable. The nice thing about these individual specific effects is that after we do the estimation, these effects can be estimated as this. So basically, if we take the average of all the variables and we put here the estimated coefficients, they would simply be recovered using this formula. So in this case, these individual specific effects AI will sum up to 0 across all the individuals I. So here the summation of AI would be equal to 0. And this is important later on when we're going to be estimating these individual specific effects. So again, after we estimate the time d-mean uh, models or transformation, we would be recovering these individual specific effects and we could actually be looking at them. Instead of doing a fixed effect within estimator, we can do a completely different procedure that actually would end up with the same results. So that's what we can accomplish with dummy variables regression with fixed effects. So here what we can do is we have the original model and variables like that. But here we would be adding dummy variables d1, d2, and dn for each of the individuals. So here a dummy variable d1 would be equal to 1 for the first individual and 0 for everyone else. So d2 would be equal to 1 for the second individual and everyone else. And the final variable dn would be equal to 1 for the nth individual and 0 for everyone else. So now we have n dummy variables because we have n individual. CI varies from 1 to n. We have n individuals in the sample. And so we would be including one dummy variable for each individual in the regression model. Here we need to normalize the first coefficient a1 to be equal to 0 so that the dummy variable d1 is a reference category and not included in the model, right? When we have dummy variables, we always need to skip one of them and not include it in the model, and it would serve as the reference variable here for the rest of these dummy variables. So here, the individual specific effects would be coefficients that would be estimated in the dummy variables regression. So we could just form these dummy variables and estimate the coefficients on them. And I will show you practically that the fixed effects within estimator that we discussed on the previous slide would be equivalent to this regression with dummy variables for each individual to this model. So you will see that during the examples. Okay, so let's do the example. Here we have panel data for 3 years and 54 firms. And here we have firm log of scrap rates would be explained by whether a firm receives a grant and the total hours of training. Here we would also have dummy variables D88 and 89, dummy variables for each year. So here's how panel data looks like. So here F code would be the firm code, and we would have data for 3 years for the first firm. This would be the second firm, and this would be the third firm. And these would be the years in the data. And here we would have log of scrap rates here. And this would be total hours. These would be dummy variables for each year. Notice how in 88, that's a dummy variable equals to 1. And here dummy for 89. So in year 89, this dummy variable would be equal to 1 for everyone in the sample. So these two variables would not vary based on individuals, only over time. And these are basically, have the firms gotten any grants? They happen to be 0 for these first firms, but there's some ones in the data as well if we look at all 54 firms. So a question that we have is, do firms that have more hours of training or grants have lower scrap rates? Basically, do they have better productivity? So these are the original variables. Sometimes during the analysis, we would be forming different variables here. So for example, we could be calculating the average over time for this individual, for this firm, in this case, for this firm. That would be the average for this. This would be the average of this firm over time. This would be the average of this firm. We could also calculate the overall mean, overall average across all of the firms. And so we would be using these averages as we're doing the transformation to estimate these models. So let's talk about means and variations for panel variables. So here, not only that we calculate a mean, that's like an overall mean, but we can also calculate different standard deviations here and these different variations that we have. So notice here what we would have. The standard deviation, that is the between standard deviation, is this number, and the within standard deviation is 0 for the F code variables. That is the firm code. Now, no one would really calculate means and standard deviation of this variable, but it just shows you that the between variation is all of the variation and it has no within variation. Why? Because F code does not vary over time. It's the same for each firm, and it only varies from one firm to the next. On the other hand, if we have year, year does not vary between the firms, right? It's the same year for every firm, but it only has within variation because we have 3 years of data, so it would change over time. So this shows you an example of a variable that would only vary between the firms or within within the firms, or basically over time. Again, these are not true variables. They're just the indicators that help us set up panel data. But here's a real variable. So that's the log of scrap rate. So here we would see that the log of scrap rate, the between variation of 1.43 has higher standard deviation than the within variation. So what this tells us is that there is more variation between the firms than within a firm. So again, these scrap rates differ more across the firms, like between the firms from one firm to the next. Then over time, it changes within each individual firm. And that's how this variable looks like. In terms of total hours of training that they have, we see that these two numbers, 2106 and 18.58, they're almost the same. So this means that the total hours of training have almost the same variation between the firms, from one firm to the next, and within the firms over time. So let's consider pooled OLS between estimator and first differences estimator. So for the pooled OLS, this is the model that we would be estimating. So again, we would be ignoring the fact that it's panel data. We would just estimate it across all of the firms and over time. Then we will estimate the between estimators. So we would be taking the averages of each of the variables here over time, and we would be estimating this model. So that would collapse our data over time. It would collapse it to one observation per firm. And we would also have the first differences estimator, where each variable would be minus the variable for the same firm in the previous year. So we would do this transformation to the dependent variable and all of the independent variables. So notice that in the first differences estimator, the time dummies are differenced out and cannot be included because they vary deterministically from one year to the next. So these are the models that are being estimated for the pooled OLS estimator and the between estimator. So here we have the pooled OLS estimator. Here we have the between estimator. And this is the coefficients that we have here. So again, for the pooled OLS model, it would stack the data for individuals in year, and it would estimate the models by OLS. And the results would show the effect of one additional hour of training across firms and over time on the log scrap rate. So that would be this coefficient here, but this coefficient is not significant. So again, we will be showing the effect of one additional hour across firms and over time because we have this pooled OLS model. The between estimator, on the other hand, would use the averages of variables over time for each firm. So even though this says LSCRAB, this is actually LSCRAB bar, and this is total hours bar. So this is the average of these variables that was used. And here the results will show the effect of one additional hour of training for a firm in comparison to another firm on the log scrap rate for this firm in comparison to the other firm. So here again, when we interpret, we would be looking at the differences from one firm to the next. So what would happen if a firm gets one additional hour of training? What would be the effect on scrap rates? So we're looking at this coefficient here, and it's not significant again. We now would look at the first differences estimator. So the first differences estimator used D of scrap rate. So this is the difference from this period and the next. And here we also have these differences. And this results will show the effect of an increase in total hours of training from one year to the next year for the same firm on the change in log of scrap rate from one year to the next. So again, in this example, we do not have a significant effect here. But again, this will be the difference, the effect of an increase of 1 hour of training from this year to the next year on the log of scrap rates from one year to the next. So now here's the fixed effects within estimator and the dummy variables regression. So for the fixed effects within estimator, here we have the time demeaned variables. So here we have the variable minus the average, and this average is taken over time. So that's the dependent variable. These are the independent variables that we have here. So after we estimate this model, we can recover the individual specific effects as this using this formula. So basically, we will be taking the average of each of the uh, variables over time. These are going to be the estimated coefficients from the regressions, and we could basically recover these individual specific effects. And they will be summing up to zero. In the dummy variable regression, this is how we're going to be estimating. These are the independent variables. And then we would be putting here dummy variables for each of the firms. So n would be equal to 54 because we have 54 firms. So we would have one dummy variable for each firm that would be equal to 1 if that's that firm and 0 if it's any other firm. And here this A1 coefficient would be normalized to 0 for the first firm. Um, so notice how here the coefficient for the first firm would be normalized to 0. And here in the within estimator, all of these individual specific effects would sum up to 0. So because of this difference here, first of all, that here they all sum up to 0, but here the first one is normalized to 0. That would change the interpretation of these individual specific effects and their values, but we can obtain one from the other. So these coefficients AI would be estimated and included in the regression output. So this is the fixed effects or within estimator. So instead of log of scrap rate, this variable is actually the log of scrap rate minus the mean for the log scrap rate for the same firm. And same with all of the independent variables. So that's the within transformation where each variable is minus its average over time. Here the results will show an increase of total hours of training for the same firm from its mean on the log scrap rate from its mean for the same firm. So this effect here is also not significant, but for the within estimation, basically we're looking at is a firm within the for a given year higher or lower than its average in terms of total hours of training? And then how would that affect the log of scrap rates? Would that be higher or lower? The only coefficient here that's significant is this coefficient on the grant in the previous period. So receiving a grant in the previous period would be associated with approximately not exactly, but approximately 41% lower scrap rates. That's how we're going to interpret this coefficient. So now let me show you the same results that we had on the previous slide. So this is the fixed effects or the within estimator. And here we have the dummy variables regression. So notice that the coefficients here are absolutely identical between the two models, but the dummy variable regressions also includes this coefficient here. So these dummy variables here, this is a dummy variable equal to 1 if the firm code is this. This is dummy variable is equal to 1 if this firm code is equal to this number, else is equal to 0. And this is the firm code, basically the dummy variable for the last firm in the sample. So here we would be having also, because we have 54 firms, we would have actually 53 coefficients estimated. Now, I include only 3 of them, but typically we don't include them because they're just too many. And that's why they're typically not included when presenting the results. So again, the fixed effects within estimator and the dummy variable regression would give you the same coefficients on the independent variables and the dummy variable regression would also include these coefficients, which would be the individual specific effects. So let's just zoom in and look a little bit more into these individual specific effects. I'm going to be looking at this intercept, and I would also be looking at this intercept here as well. So let's zoom in and kind of look at these, the first 3 firms in the sample out of the 54 firms. And I said that we can actually recover these individual specific effects from the fixed effects or with an estimator by using this formula where we take the averages of all the variables and put the estimated coefficients in the formula I showed you a couple slides ago. And this is how we're going to be calculating these individual specific effects here. They're not reported as part of output, regression output, but you could go back after estimating the model, you can recover and estimate those. Now, these are the dummy variables that are actually included in the regression with dummy variables. If you go on the previous slide, these are exactly the numbers that I had included, then we normalize the first one as 0. So these individual specific effects, we have only the first 3 of them. We have 54 of them, but all 54 of them would sum up to 0. Whereas here we have the first one equal to 0, and the rest are would be interpreted in comparison to this one. So because for the within estimator, the individual specific effects sum up to 0, this is the interpretation. Log scrap rates for the second firm are 0.45 higher than the average log of scrap rates across firms. So this is how we're going to interpret this coefficient here, is that there's something about the second firm that makes these scrap rates to be higher than the average firm by 0.45. These ones are lower than the average firm, and these ones are higher than the average firm. Again, these are unobserved factors. We don't know what it is, but we know there's something about that firm that makes their scrap rates higher. The way we would be interpreting, say, this individual specific effect, that's the coefficient here, is because we normalize everything. We normalize this coefficient to be equal to 0 for the first firm. We need to interpret it in comparison to this reference category. So here we would be saying is that log scrap rates for the second firm are 3.73 higher compared to the first firm. So this is in comparison to the first firm, where this one is in comparison to the average scrap rates for the firm. So because of this different normalization that all of these 54 effects sum up to 0, but this one is normalized to 0 and the rest are in comparison to that, we want to see what's the correspondence between them. And the correspondence is the following. So basically, if we want to calculate an individual specific effect plus the intercept, that would be the specific individual specific effect plus the regression intercept that we see here. That would be the individual specific intercept for that firm. So what we're going to find is that if we sum up this plus this, that would be exactly this plus that. So this plus this is equal to this plus that. So this plus this would be equal to this plus that. For the second firm, we would have this coefficient plus the intercept would be equal to this plus this. And for the third one, this plus this would be equal to this plus that. So basically, we just have different normalization, but because of, these summing up to 0, but this one being normalized to 0 just for the first one. But you can basically obtain one of them from the other very, very easily. So again, the point of these individual specific effects is no one typically reports them in tables in research papers because there are just too many of them. There are as many as the number of individuals or firms in the data. But if any firm like that is of interest that we want to concentrate on, we could go back and check the individual specific for that firm and observe whether or not they have higher or lower scrap rates than the average or in comparison to the first one, depending on which model you estimated. Another thing to notice here is what is the R square in each of these regressions. So here, let's talk about the R squared for the within estimator versus the dummy variables regression. So in this case, the R squared would be higher for the dummy variables regression than the fixed effects within estimator that only explains the within variation. So let me show you why. For the fixed effects within estimator, we have that the model or explained sum of squares equals 7 and the residual sum of squares is 24. So the R square is the explained sum of squares divided by the explained plus the residual sum of squared. So if we plug in these numbers, we have an R square of 0.22. For the dummy variable regression, the model or the explained sum of squares is 287, the residuals is 24. So the R squared here would be equal to 0.92. So how come we have much higher R squared for the dummy variables regression than the fixed effects or within estimator when we essentially estimate on the same regression, we come up with the same results and the same coefficients. Well, the reason for that is that we have the same residual variation in both of these cases, but the variables are demeaned for the fixed effects within estimators. So instead of scrap rates, we have the scrap rates minus the average of the scrap rates. So there's less total variation to be explained. So you see like how the model variation, the model sum of squares is equal to 7. So uh, so in this case, we would have, in this formula, we mostly have residual variation that leads to this lower R square. On the other hand, there is more variation for the dummy variables because these variables are not demeaned. So now we have much higher variation that we explain with the model. And these dummy variables actually help to explain the model variation, leading to higher R squared. So if you put in dummy variables in the regression, you will basically see very, very high R squared because these dummy variables are explaining a lot of the variation. Because you're saying there's something about this firm that we don't know what it is, but it helps explain the dependent variable, and that would be true. Um, Even though we're not going to be modeling this with the other independent variables, it's just because we have a lot of dummy variables that would be explaining variation. So let's continue to have a little bit more discussion on the fixed effects estimator. And so one very important thing is that the original model would need to have exogeneity where the variables are not correlated with the error term, because if they are, we would be having biased results. So that's very, very important. Um, what we talked on the previous slide was that the R squared for the d-mean model that uses the within estimator would not be appropriate because the variables are d-mean. So this so they would only show the within variation, not the overall variation. So if we're looking at the R square, it's actually only explaining the within variation from uh, from one year to the next within the individual and not between the firms. And that's why we would be having lower R squared. Another point that we talked about is that time invariant variables cannot be included because they drop out, they get differenced out. But if we have interaction terms with time invariant variables, that could be included in the model. And another point here is that variables that change deterministically over time, such as experience that increases by 1 year every year, such variables cannot be included in the model because, again, they would um, all result in if imperfect collinearity. So we would not be able to include such variables in the model. And another point to make here is the fixed effects versus the different first differences estimators. So how these two estimators compare to each other. So they would actually be identical when we have two time periods. So let me show you why. The first difference, which we have delta yt is equal to yit minus yit minus 1. So this is the first differences. For the within estimator, we have the time d-mean variable. So here we have yit minus yi bar. So this is the average. Well, what's the average if we have only 2 years of data? That is the value in this period minus the value last period divided by 2. That's how we calculate an average. So if we actually rework this expression a little bit, this is what we find. Well, besides that it's divided by 2, which wouldn't make a difference for the coefficients, we would have that this is exactly equal to this expression. So this is why these two estimators would be identical with two time periods. Now, when we have more time periods, so t would be greater than 2, then which model should we use? Many people use the fixed effects model because it's more efficient if we have classical assumptions hold. But first differencing may be better if there are many time periods and strong serial correlation in the errors, which means that the errors are related from one period to the next. So again, if we have many time periods and we have these errors being correlated over time, we may be better off using the first differences estimator. So here is the final estimator that we would be considering for panel data models, and this is called the random effects estimator. Here we're starting with the same panel data model. So notice here that we still have these individual specific effects AI. But here the random effects assumption would be that these individual specific effects are assumed to be random and not correlated with the independent variables. So here the covariance of each of the independent variables in this individual specific term would be equal to 0. So this one would not be correlated with this independent variable, would not be correlated with this independent variable here. Now, even though this individual specific effect is not correlated with the independent variable, uh, the error term, which is the composite of these two terms now, would be serially correlated within the individual, which means it's going to be correlated over time. So let me show you why. Here we have the covariance. This is the error term in one period, and this is the error term in the previous period. Well, if we assume that the individual specific effects are not correlated with this idiosyncratic error term, we still would have this one dropping, this expression reducing to the covariance between AI and AI. Basically, this is the variance sigma squared of A. So here the individual specific effects would be correlated within the individual over time. So now we have this being the variance of A, of the individual specific effect. So under the random effects assumptions, again, the independent variables will be uncorrelated with the error term. So the pooled OLS will provide consistent estimates, but they would not be efficient estimates. And so when using OLS, we would need to adjust these standard errors because they are serially correlated over time. So the transformation for this model would be the following. And the reason for this that we're going to be doing is that the new errors would not be correlated. So here, this looks almost like the within estimator or the fixed effects estimator. The only thing is that instead of having yit minus yi bar, we have this theta here multiplied the average here. So otherwise, if we didn't have the theta, we would have exactly the within estimator. So I repeated again the random effects estimator here. So this parameter theta, that's the random effects parameter, it could be estimated after we estimate this model, and theta would be equal to 1 minus the square root of sigma squared u divided by sigma squared u plus t times sigma squared a. So this would be the variance in the idiosyncratic error u. This would be the variance in the individual specific effect. So now, when would theta be equal to 0? So theta would be equal to 0 if this is close to 1. This expression is close to 1. And this would be close to 1 if this variance is very high and this one is very low. Because if we have this variance very high, that would be equal to 1. 1 minus 1 would be equal to 0. So when the variance of the idiosyncratic error term is high, but the variance of the individual specific effect is low, we would say that AI is not important. The individual specific effect would not be important. And if they're not very important, these would and if the individual specific effects are not important, this would correspond to the pooled OLS model. Why? Because here, if we have this being equal to 0, we would basically just have this and this variable here and this variable here. We would not be subtracting anything if theta is equal to 0. And if you look carefully, this is exactly the pooled OLS model, the first model that we talked about here. Now, on the other hand, if we have theta equals 1 right here, that would be exactly the fixed effects within estimator, right? If this is equal to 1. Well, how would we get this theta to equal to 1? This means that this expression needs to be close to 0. And how that would get close to 0 is if this variance here is very, very high. This means that the individual specific effect would be very important. And so that makes sense that if we have individual specific effects, we need to use the within estimator because it actually handles it very well by differencing it out. And if the individual specific effect is not important, that's what tells us that we can just go ahead and estimate a pooled OLS model. So this random effects estimator would be a weighted average of the pooled OLS and fixed effects within estimator, basically. So it will be a number somewhere between 0 and 1, and we can estimate and see what it is from the model. One advantage of using random effects estimator is that it can include time invariant variable because it's multiplied by theta. So in this case, we can also keep the time invariant variables. So for our particular example, here's the random effects estimator, and this is the model that we would be estimating here. So notice that we would be estimating the coefficients that I'll show you on the next slide, but this theta also gets estimated and reported as part of the output. So here, when we have random effects estimation, the output reports that sigma of A is 1.39 and sigma of u is 0.51. So here you see that the individual specific effect would be more important than the idiosyncratic term. So basically there is more standard deviation or variance here than here. So the individual specific effects seem kind of important. Let's calculate the median for this theta parameter, the random effects parameter. So I will use the formula from the previous slide here and just substitute these numbers here for the sigma. I would square them, and t is equal to 3 because we have 3 years of data, and we would calculate 0.79. So this 0.79 was actually the median theta, and that would be closer to the fixed effects model than the pooled OLS model. So this number again is much closer to 1 than it is to 0. This means that the individual specific effects here are more important, and so that's why we have a higher number here. And one side point to mention here is that theta actually denotes what we call in the lecture AI, it denotes them as UI. And when we call here UI, it denotes them as EI. So there may be a little bit of confusion over that, but this is how this theta is calculated, the random effects estimator. If we look at the results here, what we see here is that for the random effects estimator, for each additional hour of training, the scrap rate is lowered by 5%. So the coefficients on the other variables are not significantly different from 0. Okay, so now we talked about fixed effects and random effects estimator, and the question is, which of these two estimators would we actually use? So the Hausman test is used to decide whether to use the fixed effects or the random effects estimator. So here, the null hypothesis would be no correlation between the individual specific effects and the independent variables. So this is actually the assumption, if you remember, for the random effects estimator, that there's no correlation between these individual specific effects and the independent variables. And here that would mean that the fixed effects and the random effects coefficients would not be significantly different from each other. They're going to be very similar. The alternative hypothesis is that there's correlation between the individual specific effects and the independent variables. So in this case, the fixed effects and the random effects coefficients would be significantly different from each other. Um, and so in order for us to test these hypotheses, we would be calculating the difference in the random effects and the fixed effects coefficients. So here we would have all the beta for the random effects estimator and the betas for the fixed effects estimator and their covariances. And the Hausman test statistic, you see, has the difference between these coefficients here. So that's prime, which means transposed. And here we have the variance um, for the coefficients for the random effects and the fixed effects estimators, and then we have this difference again. So this is how this test statistic actually look like as far as an expression. That would be distributed as chi-square variable, and we could be running this test, this hypothesis test. Okay, so let's go over the different estimators and what's true for them under the noun, the alternative hypothesis. So here we have the two estimators, the random effects estimator and the fixed effects estimator. If the H0 is true, which means we do not have correlation between these individual specific effects and the independent variables, here we would have that both of them are actually consistent, right? Because we don't have that these individual specific effects would be correlated, that would be part of the error term would be correlated with the independent variables. Therefore, we would have consistent estimators. But the random effects would be efficient, and here we would have an inefficient estimator. Now, if the HA is true, only the fixed effects would be consistent estimator. The random effects would be inconsistent because it actually assumes that there's no correlation between these individual specific effects and the independent variables. So when there is such correlation, that it would be an inconsistent estimator. So now which one would we pick? If the H0 is true, then because both of them are consistent, we would want to pick the efficient estimator, which means the random effects estimator. But if HA is true, the only one that we can pick is the consistent estimator, so we would go with the fixed effects estimator, right? Because our first priority is to have a consistent estimator, but if both of them are consistent, then we should concentrate on having an estimator that is efficient, which means lower variance. So if the Hausman test statistic W that I showed you on the previous slide is not significantly different from 0, then both of these estimators would be consistent, and the random estimator would be used because it's more efficient. So again, this would be right here. If it's the Hausman test statistic not significantly different from 0, we would be going with the random effects estimator. But if the Hausman test statistic is significantly different from 0, only the fixed effects estimator is consistent, and therefore it should be used. So basically, in other words, this Hausman test evaluates the consistency of the random effects estimator against a less efficient fixed effects estimator, but that is known to be consistent. And how we do this test is we're comparing the coefficients with fixed effects and random effects, because we know that these coefficients for the fixed effects are consistent. Therefore, if the random effects coefficients are similar to them, well, switch to random effects because they would be more efficient. But if they're not similar to the fixed effects, this means they're not even consistent. So we should be using the fixed effects estimator. So just to say that the individual specific effects typically are correlated with the independent variables, that seems to be, for the majority, most reasonable assumption, which would make the fixed effects estimator more appropriate in most practical applications. But you always need to test with the Hausman test which one is uh, you would need to test which one, the fixed effects or the random effects, before you decide, which one you would report in the research study. So here's how the Hausman test would look like. Here is the results that I showed you before for the fixed effects and the random effects. And so what this Hausman test is going to do is compare this coefficient with this one, which seems similar. This coefficient with this one, well, it's somewhat similar. This one with this one, it's still kind of similar. This one is a little bit more different. And this one seems a bit more different, but again, the value is a bit higher. So this is how we are going to be comparing now these coefficients to this whole set of coefficients to this whole set of coefficients. But we want to know, are they really significantly different from each other? And so how we do that, they appear to be similar, but we would be forming the Hausman test statistic, which would be 1.81, and the p-value would be 0.91. So basically, we would be going with the null hypothesis here because the p-value is very high. We cannot reject the null hypothesis. So there's no significant difference in the fixed effects and random effects coefficients. So both of these estimators are consistent. So in this case, the random effects estimator should be used because it is more efficient. So this is again one of the more rare cases where we have that the random effects estimator should be used, and that we have a reasonable assumption of these unobserved effects to not be correlated with the independent variables. Again, typically the fixed effects estimator is more appropriate in many of the cases, but you need to test in your particular data set. Okay, so this concludes this presentation. As far as review questions, describe overall between and within variation. Describe these individual specific effects. how are these effects recovered after estimation, describe different estimation methods for panel data models, all of these estimators that we talked about, then compare the fixed effects within estimator with dummy variable regression, and describe the Hausman test for fixed versus random effects, and what assumption do these estimators make about the individual specific effects. So thank you very much for watching.